The next thing with profiling that we want to decide on is whether we want to perform instrumentation or event monitoring. Instrumentation is where we're going to insert code into the code of the program. That is, we're going to add additional instructions into the program to collect the execution characteristics that we're interested in. So we're going to interleave our code, our profiling code, with the code of the program. So we're necessarily going to be introducing overhead when our code is executed. The alternative is to perform event monitoring, and this is where we're going to profile certain events that are external to the executing program. We're not going to insert instructions into the program itself, but we're going to collect information by inserting code where the program experiences external events. Like we're going to, when we access the operating system or when we access a service in the runtime, we can insert code there to collect information about when the program accesses these services. We can record operations, timings, or counts that in the runtime that execute concurrently with the program, but on different threads. So it's not part of the program, but it executes in the background. Things like garbage collection, operating system access, access to libraries, multi-threaded access by different parts of the program or different services the program uses. We can also collect hardware performance counter data or hardware performance monitors, HPMs. This is where the hardware, the architecture, exposes registers in the hardware that the hardware automatically increments when different events occur. There's a wide variety of events that can occur that the hardware records, things like instruction count, number of cycles, branch accesses, branch misses, branch miss predictions. In that case, caching information, level 1, level 2, level 3 cache, accesses a wide variety of instruction behavior. And this is a sample base. These are events that occur when a counter exceeds some threshold. Signal is raised, and you can collect profile information when that occurs. Both instrumentation and event monitoring, any type of profiling, has the chance of perturbing the behavior that we're trying to measure. If you insert instructions anywhere in the program, if you do, you're trying to capture behavior of the program, when you impose more instructions, more operations for the processor to perform, you're necessarily interrupting the program to do so. And that may perturb, that may change the behavior of the original program. And so you have to really think hard about what you're measuring and whether your measurements are going to change the behavior that you're trying to capture. And for an example, when you're measuring hardware performance counters, when you go to collect the data out of the register of the HPM, the code that you execute to extract that data is also incrementing the program counters, incrementing the performance counters, the HPMs themselves. So you just have to think hard about what you're measuring and how to do it in a very lightweight, non-intrusive way. We described and discussed the adaptive optimization system in JIKES RVM in previous lectures, but lots of runtime systems for high-level languages use adaptive optimization. Typically, we're going to sample the system in some way and use that sample, those counts, to predict what the future behavior is going to be. The first question we want to ask ourselves is, does the past predict the future? In program behavior, because there is so much repetition, many times the past does predict the future, and so the recent past can inform certain can give you certain information about how the future behavior is going to perform. But what's the goal of these systems is you're introducing samples, you're making these decisions about future performance, and then you're trying to decide whether if you optimize the code, whether you can reduce that future performance um, uh, uh, time so that you can improve overall performance. And doing so by applying the optimization and reducing performance, the benefit you get has to amortize the cost of applying the optimization and the sampling that you're introducing to the program. So again, we want to sample the program, use the samples to predict the future. Once we predict the future, we use that information to decide whether we can apply an optimization and whether that optimization will pay off, because there's a cost to applying the optimization, and we need to make sure we amortize that cost. In the system that we looked at, we used sampling to identify hotspots in the program. Every so often, we would pause the program whenever there was a thread switch, and we would look at the runtime stack and see what methods were on the runtime stack. There could be, and the runtime stack again is just the call stack. So these are at any moment in time, these are the methods that have called each other to get to this program point. You have to figure out how many of those methods you want to sample. That taking the topmost method is easy, but walking the stack is actually quite challenging and time consuming. So you have to figure out how many methods you want to sample on the top of the stack to get your information. We could instead use hardware performance monitors to identify methods that are causing the most problems in the hardware, because our hardware performance monitors are measuring positive events like execution of instructions and instructions completed, but they also measure performance problems like branch mispredictions and cache misses. So we could record the hardware performance monitors and identify the methods that are causing that poor behavior, and then optimize based on try to optimize the program to try to improve the code layout and how the code is structured to reduce these problems. Hardware performance monitors are nice because they're very fast, and you can actually sample hotspots with really low overhead as well. So sampling can be really low overhead, in the order of 1 or 2% of the program performance, and it can tell you a lot of things, but it can't tell you everything. So next, I'd like to talk to you about some interesting ways of profiling the program that have shown to be effective in the literature by researchers who work in this area. There's some really clever techniques, and I just want to bring out a few here. Some of these slides were given to me from a talk that Mike Bond gave as part of his lecture at Ohio State, and I thank him for that. So as we've talked in the past in this class, we have processors today that have very long pipelines, and so we need long instruction sequences without any branches in them, so that our pipelines don't bubble, and so that we get the best throughput out of our CPUs, and thus the best performance and efficiencies. But in real life, we have programs that don't have long instruction sequences. In fact, our programs have lots and lots of branches, and so we need a way to try to identify paths through those branches efficiently. So we can identify hot paths across multiple basic blocks through profiling. If we could profile paths in a method, we could identify the sequence of instructions that are most likely to execute. If we are able to identify these paths, these hot paths through a method that are likely to be taken, we can generate traces from those programs, which is a series of straight line code through that path. However, we're going to have some guards, because if ever the control escapes the paths or the trace that we have identified, we need to handle these cases. They should be rare because, again, the traces that we're generating should be hot and so are most likely to be taken. So the original algorithm for path profiling uh, was the Ball-Laris path profiling technique. And the idea here is we assign each path a value, and that value is the sum of the edges through the path from the start to the end of the method. And we're going to number the edges between the basic blocks along this path to produce this sum, and the sum is going to be unique for each of the paths. And so the challenge here is to identify how to number the edges such that each path is unique. So in this example, with this edge numbering, the path in red sums to 0. So this is path 0. This path in red sums to 1. This path to 2, and this path to 3. There are 3 paths through this method, and we can number the edges in this way such that each path has the unique numbers 1, 0, 1, 2, or 3. The way this works when you implement it is that we have a path register, R, that's going to be incremented as it traverses the edges. It's going to be incremented by the edge value. And so we're going to inject instrumentation. This is extra instructions now that we're adding to the paths to increment R, the path register. At the very end of the method, we're going to store R once we increment it because that's going to be the count for path R. And so we can store that in memory in an array to identify our hot paths. There's lots of choices that we have here. We can put the count in an array, but if there's lots and lots of paths through our methods, then an array may not be the most effective data structure. We may have to consider things like a hash table, and then each update is going to be high overhead. So if we take a step back and we kind of look at where the overhead is going in path profiling, we can do some interesting optimizations. So first of all, along the path, we're inserting instructions that do the increment. At the very end, we're updating the path profile by writing to memory. The instructions that we're adding to the path are very cheap. They're just increments. But when we go to memory and write the value to our array, that turns out to be very expensive. So one thing we can do to optimize path profiling is to leave the instrumentation, do the sums, compute the sums for every path that are executed, but only once in a while update R. So this is a sample-based approach. Instead of exhaustive, which is what we were doing before, we can sample every so often. That is, we only store once in a while, because the store is what's most costly. If we do that less frequently, we introduce less performance overhead. And we just want to make sure that this is going to be accurate. And if the path is hot, all we really care about is identifying that one path is hotter than another so that we know where to focus our optimization energy. So we don't need to know the exact number of times a path executes. We just need to know which path is hotter than the other paths. And so, and the way we can sample this is, if you remember our lecture on the JAX-RVM adaptive optimization system, threading in the JAX-RVM is done by the runtime system itself. And so because the runtime system is in charge of threading, it forces program control to give up control of the CPU every so often. And the way we do that is we insert yield points on entries to methods and on back edges in loops. And so we can piggyback on the entry to methods to implement this sample. So only if we do a thread switch on an entry to a method, do we take the sample for the code that just completed. Mike Bond, my colleague at Ohio State, was able to show that using this technique, we can reduce the overhead from 30% down to 2%. A really nice piece of work. So the next thing we can do is we can use profile information to guide our profiling. So profile guided profiling. This is where we can take a fast profile at runtime and use it to inform how we want to do more expensive profiling. So what we're going to do here is we're going to perform edge profiling. Edge profiling is very fast. It's easy to sample, and you get a really good picture of what edges are taken between basic blocks. There's lots of ways of doing this that are very clever, and you can use any one of those to sample your edges. Once you have an edge profile, you can then use that to inform how you want to lay out your increments such that your path profile becomes inexpensive. So if you know that certain edges are hot or hotter than others, you want to assign the zero path or the zero edge to the hot edges. So if r equals 0, that's not if r is incremented by 0, we're not going to do an increment. So if we can make sure that there is no increment on the hot edges, then we can reduce the overhead of our path profile. Another very interesting approach is to turn instrumentation. So instrumentation is the idea where we insert instructions into the program to gather information that we want about the program execution characteristics. Instrumentation, though, is costly, so one idea is to turn instrumentation on and off dynamically. Now, there's many challenges associated with doing this. Figuring out when to turn it on and off is a challenge that we have to face. If we're able to do this, however, if we're able to do this, we can collect the information that we want periodically and let the program run at high speed most of the time. So you have really low overhead, but you have fine-grained instrumentation that you can collect to get really detailed information from. So you're getting detailed information with low overhead. Now you still have to ensure that the detailed information that you're getting is representative of the whole program, but that's something that we can check. So if you wanted to do this, if you wanted to turn on and off profiling, think about what this means. This means that you have certain code that you're adding to the program, and we want to, execute that code sometimes, and we want to not execute that code other times. And so you can have two versions of the method, one with instruments and instrumentation and one without, and jump between them. You can have copies of basic blocks where some of the basic blocks, they're the same, except for some basic blocks have instrumentation and some don't. We can have paths through the program, again, that we copy, that we have instrumentation on, and then when we're done, we just jump around that path to a copy of the path without instrumentation. This is called patching, code patching. We could recompile. We could have an instrumented version of a method, and when we don't want to collect profile information from it anymore, we can just recompile it without the additional instructions added. So the paper that was assigned with this lecture talks about the various ways we can do this code duplication to turn instrumentation on and off dynamically. This paper has a very clever approach to making a copy of a method, and one part of the method has no instrumentation but has a couple of checks, and that's called the checking code. And the other copy of the program, shown in pink here, is a duplicate of the program with instrumentation inserted. In the non-instrumented version, we're going to execute there most of the time, and every once in a while, our checking code will say, hey, we've executed non-instrumented long enough. Let's go take a sample of this method's execution profile. So the checking code every so often will cause the control to transfer to the checking code. We'll make a single pass through the duplicated code. The checking code will cause us to jump to the duplicated code where the instrumentation is. We'll make one pass through the instrumented code, and then we'll jump back to the checking code. And this way we can get a sample of the hot methods and actually do very fine grained instrumentation with very low overhead. Another type of profiling that I mentioned earlier is with hardware performance counters. I want to show you some examples of this. There's lots of libraries that exist today for our modern hardware that give you access to these HPMs. So if you're looking to profile in a very lightweight way, the first thing to do is check out your hardware performance monitors. Hardware performance monitors are able to sample a wide variety of events that your program or that the system is experiencing over time. On the right, we have some examples of these measurements that are being taken. There's caching information for the level 1 and level 2 caches, the energy use. We have caching information for the data cache and the instruction cache, the branch predictor, and we also have the instructions per cycle. And as you look at this trace of hardware performance counters, you see patterns emerging from the program, and this is due to repetition that's natural in our programs. And so there are these patterns that do repeat themselves, and we want to try to capture those so that you can identify opportunities for optimization. You can identify maybe cold regions in your program that don't exhibit this pattern so that you can check for bugs, and a wide variety of opportunities exist here if we can identify these samples, these patterns. So one thing that my group worked on for a while was how do we take a sample of these hardware performance counters that are reflective of the entire program. So if you look more closely, this is the same graph, but we've just colored it according to the patterns that we observe in the program. The different colors show repeated patterns. So there's 4 different patterns that repeat themselves. So these are called phases. The idea here is if you can capture the phases in your program and identify the phases that occur most frequently, you can focus your optimization effort on those phases. Actually, one of our professors, Tim Sherwood, as part of his PhD thesis, showed that you can capture these phases and both in hardware and in software by just looking at basic block profiles and comparing them for similarity over time. However, you can capture the same behavior by sampling the hardware performance counters. So some of the work that we did said, well, if there's only a small number of phases in our programs, we don't want to just sample everything. So here in this graph here, this is a simple program that iterates between 2 phases, the black phase and the white phase. And it goes back and forth, and it repeats itself. Now, if we wanted to collect a profile for this program's behavior, we could just collect periodic samples. Every few seconds, we could take a sample, and if we're lucky, we would capture the behavior of this entire program. The problem with periodic samples is that it doesn't capture the time-varying behavior of the program itself, the phases that we just saw occur in most programs. And the other problem with periodic samples is if you get the timing wrong, you could collect a sample of something that you've already sampled. So that's really just a waste. It doesn't provide you with any new information. What you really want to do is you want to profile, take a sample on each phase. So you want to identify your phases, and then you only want to sample on a phase, because then if you could record how often phases occur, then you'd have a full picture of the entire program without sampling very much. So again, if there's only 2 phases in this program, we would take 2 samples instead of sampling across the entire program periodically. So that's going to save us in our overhead, but we're going to still have enough information to reconstruct the entire program behavior. Here are some results to show you how good how well that works. Along the y-axis, we have error. So the higher this is, the worse. You want to keep your error low. Again, we're sampling, so we don't have perfect information, but we're trying to get as perfect as possible. 0 is perfect. Across the bottom, we have the percentage of the program that is sampled. If we sample the program a lot, we're introducing tons of overhead. So we don't want to do that. So we want to stay to the left as much as possible. And so if you randomly sample or you periodically sample, you never get as low overhead as if you sample according to your phases. Now, and so what this shows is that if you're able to sample based on your phases, you can sample a very small portion of your code and have very, very low error. That is very, very high accuracy. You get about a 50 to 75% reduction in overhead over periodic or random sampling. Now you have to figure out what your phases are, but there's software and hardware techniques that enable that. Another way of looking at profiling, if you're interested in understanding your programs better, is for applications that have user interaction. A user, even though we like to think of ourselves as really smart and really fast, are very slow compared to computers. And so if you have an interactivity session in your application, you can use that interactive session to piggyback profiling. So the idea here is when the user is using the program and is engaged with the program and making decisions affecting the behavior of the program, you want to stay out of the way. That way, the response time to the user is very fast. However, when the user steps back and is thinking, we call it the think times, you can put some profiling in during that time to determine what happened in the past, what's likely to happen in the future. You can do work while the user is pausing during these pause times. So what this shows here is the interactivity session in the UI of Tetris, a Tetris-like game. Across the bottom are the events that come into the system, and across the y-axis, or up the y-axis, is the event enter-arrival time. So when the enter-arrival time is very large, these are the thinking periods of the user, and we can perform our profiling there in a way that the user won't notice. All the other events that happen frequently and really close to each other is when the user is interacting with the game, and therefore we don't want to interrupt their experience. And so again, this is just a different way of thinking of when to apply your profiling so that you get good information without impacting performance or users' perception of program performance. Here's a different game, Solitaire. There's again, just different behaviors, different patterns of user think time. When there's a big delay between events, you can do a lot of work with your profiling. There's lots of profiling tools out there. I encourage you to check them out. Pin and Dynamo are dynamic instrumentation technologies. Valgrind allows you to do lots of things, but typically it's used to identify memory problems. gprof is a very good way to start to get your call graph and your timings for your functions. Every programming language has language-specific profilers. I list a few here for Java, Ruby, and Python. There's also lots of library support, as I mentioned earlier, for hardware performance monitors. There's library support in a tool called PAPI. but Perfmon, and there's just a number of different hardware performance monitors that you can get as libraries that will work on your system. So I encourage you to understand what your programs are doing. Don't just assume they're behaving the way you think they are behaving, and you can use them to figure out where your performance bottlenecks are and where your bugs are, and improve both the performance, maybe in battery consumption, as well as the quality of your code.